this is a total production. Alright, so this is going to be our third and final video for the alkyne portion of chapter 6. So in this one we are looking at hydration reactions, so we're pretty much adding water. We're individually adding hydrogen and OH, and so what we have are two different sets of reagents that we would be using. We're either going to be using hydroboration, which does an anti-Markovnikov addition, or we're going to use mercury sulfate, which will do a Markovnikov addition. So hopefully you recall when I had you use the mnemonic Merky-Mark, right? Mercury loves to do Markovnikov. So what does that tell us? Well, with anti-Markovnikov, that means of these two carbons, right, this one doesn't have as many substituent groups on it, so the OH group is going to go there, right? With Markovnikov, right, this carbon has more substituents, so the OH group is going to go there. Now, and I guess I'll show the hydrogens too. So yeah, that's what you're looking at. Okay. Now from there, you have this crazy little intermediate that forms. Right. This thing is called an enol. Right. So we're going to get the double bond, and then you'll get the OH there for the hydroboration. So you get an enol. Now enols are unique for these sets of reactions because these will actually rapidly tautomerize to a more stable form. So tautomerize. So this enol will rapidly tautomerize to its ketone form. And so just generically, that looks something like here, where the pi bond will attack the hydrogen, and then the bond between the OH will break and make a double bond there. So you go from the enol to the keto form. Now, I call it a keto form because that's generically what it's called. But the deal here is this is an aldehyde functional group. Okay, so hydroboration can make aldehydes. Now, with the Markovnikov addition using mercury, this will give us the OH there. Right now, in doing so, this is yet again also an enol, right? Enol means you have a double bonded carbon, but also an alcohol on the same carbon, right? This will also rapidly tautomerize. And so if you pay attention here, right, this double bond pretty much just shifts from between the carbons towards the oxygen, more or less. So what do we wind up getting here? We get our ketone instead, right? So these keto forms, right? Now this one actually is a ketone, right? These are what we're going to get as our major products for these reactions. All right, now, if we look at this guy, right, so this alkyne has a group on each one of the triple bonded carbons. So there is no difference in the level of substituents on the carbons. So the problem we're going to face here is that we're actually going to now get two products. So we're going to get, for our enols, I'll start with those again. So for our enols, right, you're going to get one with an OH group there, but you're also going to get one with an OH group that's at that carbon as well. So OH there, okay? And then both of those are going to tautomerize, like what we just saw, from their enol forms to the keto forms. And so what we're going to have here are two different ketone products, right? So that ketone product, right, is from this guy. And then we'll get our other one, which is going to be from this guy, so the double bond there. Okay. Now, if you'll notice, the mercury sulfate, even though it does a Markovnikov addition, it has the same problem. There's the same degree of substituents on each carbon. So guess what? You're going to get the exact same two sets of products here for this guy as well. So I'm just going to draw the products because I've already shown you the enols up here. Alright, and then lastly, wrapping this up, we have a terminal alkyne again. So now we actually do have to worry, right? We're not going to get a combination of products, thankfully. Alright, and so what are we going to wind up getting here? This will do the anti-Markovnikov addition. I guess you could think of it as AB, right? A, B, C, D, E, and K. That's the good sense way to say. So, if we think AB, anti-Markovnikov boron, I don't know. And then I just use murky mark, okay? So that means that for this guy up here, the OH is going to go at the end, and then the hydrogen's going to go right there. For Markovnikov, the OH has to go right there. So that means the enol intermediates that we're going to get, right? So you're going to lose one of the pi bonds to the addition, and then you'll get an OH here at the end for the hydroboration. So there's our enol. Yet again, rapidly tautomerizes, so pi bond attacks the hydrogen. We break that oxygen-hydrogen bond and get a double bond there. And that will leave us with an aldehyde. Alright. Next, pretty much a very similar idea here. The enol that we're going to get, right, is like this with the OH, right, as a Markovnikov addition. So there's our enol. That will rapidly tautomerize to its keto form, so that just means the double bond is going to be here now. Right, so we get a ketone. Alright, so yet again, we now have Markovnikov and anti-Markovnikov to worry about, and with these hydrations, since they are alkynes, we do have these weirdo enol intermediates that tautomerize to give us the ketones, or the aldehydes, depending on if it's a terminal alkyne or not. Alright, so that concludes the practice for Chapter 6. Adios.